Okay, today we're doing chapter 10, rotation of rigid bodies. This is going to be a high-level overview. I'm going to go over what I do to study for exams like this. I'm going to give you guys tips and tricks on how I study. And we're going to go over every important equation in this, but I'm not going to do any problems. The problems are for you guys. I don't have time to do a problem today, but if you have a special problem, I have a few in mind, so I'm going to do them in the next few days. But if you have a special problem, put it in the comments, please. I got you. But also try to do the problems on your own. One thing I want to say before we get into the sections and all the equations is I have some important videos for you guys to watch that I think are helpful for studying for exams. This video over here, I do something, it's for a different part of this book, but I think the strategy I do here is amazing. You guys should do it. It's what I've been kind of hinting at, but this is a full video that explains it. If you want to see how I remember stuff, because there's so many equations here, like look at all these equations. It goes till equation 33, just in one chapter. Do you have to remember this equation right here? This one? Probably not, but it's kind of nice to remember as much as possible. So if you need help remembering stuff, I have another video. Check out this one over here, I think. And I'm going to put some other ones here that I think are helpful that I generally use and you can apply to any chapter in this book. So right now we're going to do chapter 10. I think in the next video, since the exam is coming up, I'm going to do a big bird's eye overview of all 15 chapters. I don't think I can cover all chapters like individually. So let me know which one you think you want to focus on the most. That being said, I made a little sheet over here of all the different sections, some general ideas, some key equation, some other things over here, and then here I just pulled every equation from the book. Some of these are not important, some of these just build up to stuff, but I'm going to go through them very quickly individually. And you can try doing the same thing. And then if you know exactly what this equation is talking about, you know automatically what kind of problem is going to be using this equation. So then if you read a problem and it says something that kind of sparks a light in your mind and you imagine a problem and you connect that problem to this equation, boom, you're already halfway there. You can just isolate, look for the terms that you have in the equation and then solve the problem this way. Obviously, it's a bit more complicated than that, but if you know the name of the equation, the symbols inside, and an example problem that this equation uses, which I'm not going to do in this video, but maybe in a future video I will do, then you are very, very comfortable for the exam, and then you can proceed doing a bunch of practice problems. So we're going to start just reading very quickly the sections. We have angular position, velocity, and acceleration. Analysis model, rigid object under constant angular acceleration. Angular and translational quantity. So all of this stuff here, these three sections I'm going to put together, and they are bringing into play these three symbols. The theta is like the angular position. The omega is like angular velocity, which is like analogous to translational velocity or linear velocity. And this alpha is angular acceleration, which is analogous to linear acceleration, this regular A. So that is all these three things. This is the first third of the book or so, or of the chapter. Then they introduce torque and analysis model, rigid object under a net torque. Calculation of moments of inertia. So moment of inertia is I. It is in this equation over here. This is torque equals moment of inertia times alpha. So torque is kind of like a rotational force, you can think about it. Here is like the linear analog. It's like Newton's second law, but for rotational stuff. So you have moment of inertia, which is kind of like the mass of a rotating object, angular acceleration, which you learn in the first third of the book, and then torque, which is this thing that is introduced in like the second third of the book. Then you do some energy related stuff, rotational kinetic energy, energy considerations in rotational motion, rolling motion of a rigid object. This is like a little bit of a side chapter, but it includes energy and stuff in it. So just breaking the whole chapter down into these three main sections are very important. And I think for your guys' exam, torque is a like super important thing. But you only understand torque if you build up and learn about these things first. So that's why they introduce them first. Anyway, core idea, everything from linear mechanics has rotational twin. So x, which is one-dimensional position, turns into theta, which is like position of a rotating object. Like if you have a CD, it rotates, it moves, but it just sweeps out these thetas, these radians or degrees. V is angular velocity, omega, the Greek letter, right over here. A, which used to be linear acceleration, is alpha, the Greek letter, for angular acceleration. Mass goes to moment of inertia, and force goes to torque. So if you remember these equations in the first linear column from the beginning of the course, like the first half of the semester, I think chapter 5, then these rotational things are very similar. So just make this connection in your mind, and you don't have to remember as many things. Like you don't have to remember individual things, but keep in mind what each of these symbols means and their name. And also if you can remember their units. Anyway, here we have another interesting piece of info, rolling without slipping. Don't worry about this. This is some random bobo. Total kinetic energy is equal to translational kinetic energy, which is 1/2 mv squared over here, plus rotational kinetic energy, which is 1/2 moment of inertia I times omega, which is angular acceleration squared. So this is interesting. Don't worry about remembering it. I just put it in here because it was a cool piece of summary from the chapter. Key equations. We got torque. Here it is. Tau, Greek letter, is equal to RF sine theta. Don't worry about this FD, I haven't seen it too much before, but this sine theta also comes from the cross product, which is a multiplication between two vectors. In this case, R is a vector and F is a vector. So the cross product between those gives you the torque. Here's like Newton's second law analog. Torque is also equal to I, the moment of inertia, times alpha, the angular acceleration. And here you have two different equations for torque. So if you want to find torque, or if you want to connect these two equations and find like moment of inertia in terms of R, F, theta, and alpha, you can use these two equations here. Here's how you calculate moment of inertia. Not too important, but we can take a look at it if you're interested. Just remember I is equal to moment of inertia, m is equal to mass, r is normally equal to a distance, and this equation gives you moment of inertia. This is the parallel axis theorem. I have not seen this before, but it scares me, and I don't want to show up on the exam and be like, bro, I read the parallel axis theorem, but I kind of skipped over it. So out of fear, I would probably just learn this, like, I don't know, before I go to sleep tonight, just search up parallel axis theorem on Wikipedia, watch it, check on YouTube, parallel axis theorem, classical mechanics problem, university physics, or something like this, and watch one really quick, just so I have something to play with in my mind. If you forget it, don't stress about it. This is going to be like 1% of the exam. Then you have rotational kinetic energy, similar to translational kinetic energy, but it is now 1/2 I omega squared. I, again, moment of inertia, omega, rotational velocity. Then rolling condition, V center of mass, so the velocity at the center of mass is equal to R times omega. Interesting, but I'm going to skip this because I think it's more nicely introduced later in the equations from the book. And then this thing, rolling down an incline, I don't think you got to remember this. You can most likely work up to this if you know all of the other conditions and you read a problem with something rolling down an incline. These things, I think I'm going to leave them. It's moments of inertia for common things. Solid sphere has this moment of inertia. Hollow sphere has this moment of inertia. The capital M is always the total mass of the object, the solid sphere, and R is some kind of radius. So a sphere has a radius, a hollow sphere has a radius, a solid disc, so like a coin, has a radius, a hollow cylinder has a radius, and a rod has a length. So you can see these, you don't have to remember these, but just know that they relate to moment of inertia, and then moment of inertia makes an appearance in some of these equations. So if you have an object like this, most of the time you're going to pull its moment of inertia, put it into here, and find like the torque or its angular velocity or acceleration or things like this. That was a big summary that I just created very quickly. It's not about the actual chapter. Well, it is about the chapter, but it's not like going chronologically through the chapter. It kind of just summarizes things. So here I have literally every equation, one at a time. We're going to go through them very quickly. Angular position, theta is equal to s. S is the arc length, and r is the radius. So imagine you have some circular thing. I don't know. Imagine my water bottle here, right? It has a radius, r. This is the radius, from the center to one of the edges. Let's say I put a piece of tape or a marker right here and call this theta equals 0. I can rotate this theta. So it used to be here, now it's here. Maybe that's like 30 degrees, maybe 45 degrees. That is the theta, you put that here. R is the radius, and S is the arc length. If I move from here to here, this little like sweep, if I put a piece of string and mark out the like arc length that this theta sweeps on this circle of radius R, that will be this little length of string, and normally you have it in units of meters. So here you can see theta is equal to something in meters divided by something in meters. The meters cancel and you get something unitless, which is an angle. Normally the units here are degrees or radians, but I haven't seen these put anywhere. So degrees or radians are unitless, which is kind of strange, which we might get into in another video, but that's too deep for this class. Just remember theta, arc length, radius of a circle. Arc length, here it is. Literally this equation, sweep it around, you get an equation for arc length. If you read a problem and they say the word arc length, you need to automatically be like, this S means arc length. So I'm going to use this and find the arc length with this. I'm going to stop saying that word, this one right here, boom. Average angular speed. So if they introduce theta and theta is like x, like position, then the angular speed, which is analogous to the linear speed v. Look at this motherfucker, bro. Bro, this is an arc length right here. One arc length. Chill out, my boy. Okay, so omega, which is angular speed, is the same as velocity when you learned it back in the day. V is equal to delta x over delta t. Now you just change the x for a theta and you change the v for an omega, and you have the analogy for angular speed. So here is a limit equation. You don't have to worry about it. Just remember what all the units mean, all the symbols mean, and what units they have. Average angular acceleration. This is the same thing, analogous to what you learned before. Acceleration is equal to the change in velocity over time. Angular acceleration is equal to the change in angular velocity over time. Boom, here is another interesting equation. If you have the final and the initial, and you have the final and the initial time, you can find the average angular acceleration over this time period. Instantaneous angular acceleration, another limit equation. Don't worry about limits right now. Cool, we just finished the first section. Analysis model, rigid object under constant angular acceleration. I'm gonna breeze past these because they're the same kinematic equations as what you learned in the first linear portion of this before the midterm. So here you have an angular final velocity is equal to the initial angular velocity plus angular acceleration times time. You have a disk, it is spinning, it starts from rest, it accelerates for an X amount of time, find its final angular velocity. Boom, easy. Just know the names of all of these symbols. And then imagine a problem, or check your homework, or check the book and see what problem uses this. Just quickly do it so you have something in your mind on how this equation is used. Same thing here. You have a final theta. Where does the disk start? Theta initial. Where does the disk end? Its initial velocity, angular velocity, its acceleration over some amount of time. Same thing as the linear equation. Over here you have another one for final and initial, but here, check this out, you have theta initial and theta final and acceleration. So compared to the first equation where you have omega final, omega initial, alpha and time, this one you have omega final, omega initial, alpha and theta. So if you have some problem where they give you the time, you use this equation right here. If you have a problem where they use the initial and final angles, you use this equation right here. Boom, easy peasy, just plug, make sure all the units cancel out and you get the proper final expected units. Final expected units for theta is radians or degrees. For omega, it's radians or degrees per second, and for alpha, it's radians or degrees per second squared. But normally in your equations, radians or degrees are going to be unitless. You're not going to see them. You're just going to see something per second or per second squared. Hopefully that doesn't make sense, or hopefully that does make sense and I'm not speaking too fast. Rotational kinematic equation. Here's another one, final theta, initial theta, 1/2 omega initial, omega final time. So if you have the initial and final angular speeds, you can find the initial and final angles over some period of time. Amazing, we're going to the next one. This is a super, super, super important section. Angular and translational quantities. When you have something spinning, right, this bottle, it has an angular velocity, this omega, but it also has a radius over here. So this v in this equation here, the tangential speed, is the v that you feel at the tip of this. So you rotate, right? Imagine the earth, you're rotating, right? And something at the tip of the earth feels this like kind of velocity pointing this way in the direction of the angular rotation. So if you want to find that, by the way, this thing changes. So if I go closer into the center of the circle, the r reduces. If the r reduces and the omega stays the same, then the v should reduce too. So if I'm chilling right here close to the center, my tangential velocity or speed, that v, is smaller than if I was all the way out here because the radius changes. Hopefully that makes sense. This is the same thing for tangential acceleration. So if you want to convert these angular quantities to linear quantities, these two equations are immensely important. And this is a centripetal acceleration equation, which you guys remember from chapter 6, I think. Centripetal acceleration is equal to v squared, which is the tangential velocity, which you can get from this equation if you're interested, over r, and then they literally plug that in and they get r omega squared. So centripetal acceleration in terms of the angular velocity is r omega squared. Hopefully that's helpful. Just know the names of the symbols and then the equation should become a bit easier to use. Total acceleration, I think all of these symbols here are shown up here. So I'm going to leave this as like an exercise for you guys. That looks like it is the total acceleration, and it looks like it's built of components, the tangential acceleration and the radial acceleration. I don't know. So this is an exercise for you guys. Try to figure out what this equation says. If you use this stuff that you found here and maybe like draw a picture, I think you should be chilling. So let's move on to torque. Remember, we just finished the first third of the chapter. Keep in mind the little sections I showed you here. This should help you kind of organize things in your mind and kind of remember them a bit easier. Hopefully. Let me know if you have questions, though. I'll try to find some kind of interesting analogy. Then torque. Whenever I think about torque, I think about a wrench. So you have a point of pivot, right? Let's say this is the nut that you're trying to unscrew, or the bolt. And you have a distance at which you apply some kind of force. So here's the force, I'm applying the force down, and here is the R, right? So you can see torque in this equation has T, tau. It is directed in or out at the point of the nut. You have a distance, this R, it's like the length of your wrench, or the location where you press. Like if I press here, it's a small amount of torque. If I press here, it's a big amount of torque, because I increase or decrease this R. If I push a lot, torque increases. If I push a little, torque is small. All right, so check a picture, a few problems with this. And sine theta is the angle between the force and the R vector. So if I point here, this is 90 degrees. You see the 90? It's exactly perpendicular. But if I go like this, the angle is smaller. If I go like this, the angle is different. I don't know if this is a smaller angle or this is a smaller angle. You got to take a look at a picture of torque and all the vectors in there. Also for torque, remember right-hand rule. So point your thumb in the direction of R. Point your finger, your pointer finger in the direction of F. And this middle finger is going to point in the direction of the torque. So if I push this wrench this way, the torque is going to be pointing in this way. If I push outwards, or if I push this way, the torque is going to be pointing that way. Hopefully that wasn't too much, but if you know each of these symbols, don't stress about it. Just plug numbers in, see what happens. And if you have more time to prepare, just do a few problems. Analysis model, rigid object under a net torque. Net torque on a particle. So you see this big sum, it's a big epsilon Greek letter. This means add. So you have multiple torques acting. I push this thing this way, there's another guy pushing this way, so there's multiple torques. In this case, they're counteracting, but maybe there's going to be two guys pushing this way, so there's two torques pushing that way. So the torques add up there. If they're counteracting, they subtract, I think, because one is pushing one way, the other one is pushing the other way, so one of them has a minus sign. So here you have mr squared. What is this? Where does this come from? I'm not sure, but I think mass means, or m means mass, r means distance most of the time, like radius, and alpha means angular acceleration. That's all I need for now. I don't care anymore about this equation. If I need it, I'm going to pull it up and then use it in a problem. Or if I see a problem, I'm going to take notes if they use this equation. Net torque. Here we have another equation we saw before. Net torque, the sum of all torques is equal to I alpha. I is the moment of inertia. Alpha is the angular acceleration. I don't really need to know what moment of inertia means or what alpha means. Maybe it's good to remember their units. The units would be good. I think torque has units Newton meters. Inertia, I think, has units of kilogram meter squared, because I think moment of inertia is mr squared, and m has units kilograms, r has units meters. So r squared, meter squared, kilogram meter squared, I think. And then angular acceleration has units of angles or degrees, or nothing, over seconds squared. Net torque on a rigid object. This looks a little complicated. I'm gonna skip this one. It looks kind of similar to what we saw before anyway, related to this, so I'm gonna skip this one. Maybe I'll leave it as an exercise for you guys. Try to figure out what each of the symbols in this equation here, the 10.17, means. Rotational analog to Newton's second law. This equation here looks the same as this equation here, so I'm gonna skip this one as well. Moment of inertia, I is equal to big sum m, which is the mass I, r, which is a radius or distance, squared I. What does this mean? Don't worry about it. It doesn't really matter. Just remember this is the equation for moment of inertia, and you find it by doing some kind of mass times some kind of radius squared. If you're interested and you want to see how to calculate moments of inertia, there's a section where they do problems like this. Oh, here it is, section 10.6. Actually, I think we're going to skip through this section quite a bit because I don't think it's too important, but here's this parallel axis theorem, which I'm avoiding because I'm like, I read parallel axis theorem, I'm like, I don't like this, but if I see it on an exam and I avoided studying it, I'm going to be really mad. So I'm going to search up tonight what parallel axis theorem is. In the next video, I'm going to try to explain it to you guys. But for now, it just looks like moment of inertia. Moment of inertia, moment of inertia, moment of inertia. 3 equations for moment of inertia. And then here we have m, d, some other stuff. Like, I don't know what this is. We're going to skip it for now. Rotational kinetic energy, total kinetic energy of a rotating object. This is super interesting. K subscript r, which is kinetic energy of a rotating object, is equal to 1/2. This big thing right here, this big thing I think is moment of inertia, because we just saw a moment of inertia up here, this equation. It looks exactly like that, boom. So 1/2 I, and then omega squared. This is crazy. And look at it here. So this is the only equation you have to remember, 10.24, rotational kinetic energy, 1/2 I omega squared. And we already know what those symbols mean. So if I want to find the rotational kinetic energy of an object, and I know its moment of inertia and its angular velocity, boom, I could just put it in there. And I think most of the time it has units of joules for kinetic energy. But I'm just remembering this. I could be wrong. So double check, put this in your equation sheet or like write it down and try to remember it. Go back to this video if you're interested in how to remember things. Energy considerations in rotational motion. This is section 10.8, and then we have section 10.9, and then I think we're done. So we have work done by torque. Cool. This is just work done by torque. This dW I think is a small amount of work. So if I remove this d, I just have W is equal to R d theta. Or that's not R, that's tau, so that's torque. So I think d, I can remove the d from the theta because d just means a small amount. So a small amount of work is created by a small change in theta. But if I just have the equation simply, it's going to be W equals tau torque times theta, which is the same thing as what we learned torque was back in translational or linear part of the class. We had work is equal to force times distance. Now we learned in the rotational side of things that torque is kind of like a rotational force and theta is kind of like a rotational distance. So it's the same equation as what you learned in the linear part of this class. That's amazing. And now I know what all these symbols mean. Power delivered by a rotating object. P, I'm assuming means power. It is the derivative of work with respect to time. Or here they write it as tau times omega. So if I want to find the power of something with a torque acting on it going an omega, an angular velocity, I can use this equation. That's amazing. I don't know what units power has. I got to remind myself, I think it's watts or something like this, like joules per second, right? Because work, I think, has units of joules, and T has units of seconds. So joules per second, I think, is defined as a watt. But I'm not sure. I'm going to take a drink of water because I've been yapping for a minute. Work kinetic energy theorem for rotational motion. I'm going to skip this one too, guys. We're going to go here. Condition for pure rolling motion. Vcm is equal to r omega. V, I'm assuming, is the velocity at the center of mass. R is the radius of some object that is circular, that is rolling, and omega is the angular velocity of that object. Linear acceleration in pure rolling. So the acceleration at the center mass, which is linear, is equal to r, the radius of the rolling thing, which is normally a circle or a cylinder or something with a radius, times alpha, the angular acceleration of that rotating thing. Kinetic energy relative to contact point. Kinetic energy 1/2 I p omega squared. I don't know what this is. I'm gonna skip it. But IP is interesting. Total kinetic energy of a rolling object. Boom, I think we saw this before. Kinetic energy ICM omega squared plus 1/2 mv squared cm. So it's like translational kinetic energy plus rotational kinetic energy. Super interesting. This equation for sure you might see in a problem. I think you're gonna see this one. Total kinetic energy. Alternative form. Here's an alternative form. So these two equations probably important to remember or just like figure out what equation or what problem uses them. Speed of center of mass on an incline. Wow, I'm not going to remember this, so I'm going to just search up a problem that asks you to find the speed of something center of mass while it's rolling down an inclined plane, and that is the whole chapter. Sorry I went through this very quickly, guys. I'm trying to help you guys out, but I think this method is super important, and it gives you something to do. Some people are kind of unsure how to study. Literally just go through the book, go through your equation sheet, and then write the name of the equation and each of the symbols and the units, and then connect that equation to a problem, and then do that problem. Also, do all the problems in the final practice final exam, do all the problems in your homework, do all the problems in the book. I know this is a lot of work, but just try to rush through it. Try to push yourself. You guys got a lot of time right now. Just focus. Every day, try to cover a chapter. Actually, every day I would focus on the whole book. So I would look at the book fully and be like, where am I struggling? Boom, start doing that. Go through every equation in the chapter as I did here. Let me know if you guys have questions or problems. I will help you with anything. Just put a comment in this video. And good luck studying, guys. Stay hydrated. Talk to your friends and family. Relax. Go on a walk, man. Don't go on your phone. Go on a walk and just think about rotational motion. You're going to be chilling. It's almost summertime. The semester's almost done. There's birds in the air. It smells good. You guys are chilling. All right? I'll see you guys in the next video. Peace.